Welcome to lecture number 10 of module 2. In this lecture we will see the small signal stability. In the previous lectures we saw this transient stability, and then we had what are the ways to improve the transient stability. We also discussed along with the various methods to analyze and to see the stability of the system. Small signal stability, as again just I want to recap because already I have given this definition. So it is the ability of power system networks to maintain synchronous when subjected to small disturbances. Again, these small disturbances, it is not continuous, it's a sudden small disturbances. So what we can do, since the disturbance is small, so we can utilize the linearized analysis of the dynamical system around an equilibrium operating point. I also discussed the various modes of oscillations. I discussed the local modes of oscillations. Here this is the local modes. Here I also said this intra-plant modes of oscillations, inter-area modes of oscillation, and the transient modes of oscillation. So the local modes of oscillations, the frequency is normally lies between 0.8 Hz to 1.8 Hz. However, your inter-area modes of oscillation, it is lying between 0.2 to 0.7 Hz. In inter-area modes of oscillation, again I want to tell you that's the two regions, if they are oscillating to each other, then it is called inter-area modes of oscillation. The local modes are this individual machine oscillation, that's modes of oscillation. It is basically one unit of any plant is oscillating with the rest of the system, and that is frequency is this. So intra-plant modes of oscillation, if the various units of the same plants, if they are oscillating to each other, then it is called intra-plant mode of oscillation, and the frequency is normally 1.5 to 3 Hz. To understand this dynamic stability, let us see a practical system that is we have analyzed. It is a Kaiga nuclear power plant which is in Tamil Nadu. This is a Kaiga nuclear plant and its rating is 220 megawatt, and there are two units. Here the two units are here. So all these are the generators. So there are the two hydro generators. One is at Katra and another is Kudsali. This is a hydro generators and the rating is 120 megawatt, and this is generating 150 megawatt. When the lines that is connecting between this Kadra hydro as well as this Kudasali hydro, means this line as well as this line, if they are not in operation, means if they are in outage condition, then whole power of this Kaiga will be evacuated through this double circuit line here from Kaiga to Guttur, and finally it is going to Raichur and also Raichur thermal power station. So at this station, during that condition, when the line this from, you can say bus 1 here, this is your bus 2, and if this is a bus 3, so line between bus 1 and bus 2 as well as the line between bus 2 and 3, if they are in outage condition, so whole this power will be evacuated through this line, and the power station which is here generator is experience that there is a severe oscillation. Then that is basically case of your small signal stability, or you can say dynamic stability. So here the system studies, in this case we studied this system, and finally we found this is the due to the proper tuning of the power system stabilizers. The system studies is the part of a big network, of course whole this is a southern region, and only we took the small portion of the system where the two generators nearby of the Kaiga have been considered. The Kaiga, this power station was equipped with this amplifier of automatic voltage regulator, that's AVR, and has a PID, that is a proportional integral derivative characteristic, whose parameters can be varied using the selector switch. Means using the various selector switch, the parameters, you can say gain and the time constant, can be varied. The actual setting are collected from the site for the study, and the generators at this nuclear power station show a vigorous power oscillations if the two neighboring hydro generators are disconnected and the power is evacuated through the double circuit line, as I said here, means this is a double circuit line, this as well as this. So this total power is coming through this line, and then it was observed that oscillation of 0.8 to 0.8 Hz. It was measured, that oscillation. So you can see this oscillation is nothing but it is coming out to be in this range, means it is a local modes of oscillation, means the unit at the KEGA they are oscillating with the rest of the system. So it was this, we just explored what are the possibility. First we verified with the collected data, and then we try to tune the power system stabilizer. You can see here, this is your case when the basically it is the load angle delta at the KEGA at the Kudasali, just we simulated. If the line, as I said, the two lines, if they are out, that's the KEGA Kadra line as well as the KEGA Kudasali line, then at that time here what we did, we tripped the line and we found, you can see this is oscillation, here it is observed, and that oscillation is conforming with the actual measurement. So this here it is a damped out, no doubt, but this is a persisting oscillation and that is not required, that is not good for, especially for nuclear power station. So it is found that there is some dynamic stability in the power system, they are keep on oscillating, and then we should go for the proper damping or proper measurement as well as the proper mitigation techniques for these dynamic oscillations. To understand how we can simulate, how we have simulated this studies, let us go in certain mathematical background, and the background means we have to write the dynamic system behavior in terms of differential equation. So a dynamical system can be described by set of first order differential equations in state space form. So here your, just I have written, this is your equation 1, here another is your equation 2. X is here that is used, that is the state, the vector of state variables, whereas your u is a vector of inputs, your y is vector of outputs, and f and g are the nonlinear functions as here. Here x, just we are denoting, this x is nothing but it is a various x, means your x1, x2, and it is, let's suppose if there is n state, so this is a vector. Similarly, your y is another vector, it is your y1 to your ym, let's say your m is output, here n is the state of this. Similarly your u can be a different one, that is your u1 to your uk. So these are the various state, the various vectors. So this is your state vector, this is your output vector, this is your input vector. Now from this two equations, although this f and g, they are the nonlinear equations, if we are considering here as a time, let's suppose here t is also considered in this x dot, means this f is a function of x, u and the time, then this is a normal description of a dynamical system. But if this, it is independent of time, means if your time is not taken into account, then your x dot, that is your f x u, it is nothing but it is called your, it is your autonomous system, it is declared. Means here if the derivative of state variables are not explicit function of time, if your this derivative is not a function of explicit function of time, then this system is said to be autonomous function, that is your autonomous function. From this equation we can get the equilibrium or the singular point, and that can be obtained by this putting your x dot is equal to 0, means all the derivative of the state variable, and again this derivative is the derivative respect to time. So x dot is nothing but here it is your d upon dt x. So if it is 0 for all the states, then it is called the singular point or equilibrium point. If your function here, this f, it can be a linear or non-linear. In this case in power system it is non-linear, but if it is a linear function, then you will have only one equilibrium point or singular point. However, if you are having non-linear function of this f, it may have more than one singular points or equilibrium points. So that's why in the nonlinear system the equilibrium point may be several, but in the linear system it is one, and that is your unit. Now the question again comes into the picture, what is your this x, why this is a x at all? So let us see what is the states of any system. So a state of a system represents the minimum amount of information about the system at any instant in time t0 that is necessary so that its future behavior can be determined. So this x naught is the minimum, this x is the minimum information. For example, if you remember in the load flow, normally we take this voltage and angle as the state variables because these are the only two minimum information from which we can calculate the rest of the system parameters, or you can say performance. For example, if you are knowing V and delta at each bus, knowing your the topology, knowing your network configuration, their parameter etc., that is fixed, we can calculate all the parameter like your P loss, we can calculate the Q loss, we can calculate the power flows in all the lines, we can calculate the reactive power flow in all the lines. So these are the things we require in any power system. We can calculate the reactive power generation of all the buses, especially in generators, we can calculate this. So these two are the state elements, you can say states of the power system, that is for your, you can say, steady state information. So these two are the minimum. I am not telling that we can get all the information. So here this V and the delta are the state variables for the steady state. Similarly, for the dynamical system, we require the states that represent the minimum information of the system by which we can get the complete information, this behavior, future behavior of the system that can be determined. So this x is your nothing but state vector. Now the previous equation, here we had the equation number 1 and 2, they are the nonlinear. As I said, if the disturbance is small, so we can linearize these two functions around some x naught point, and that here we want to linearize, means for a small disturbance resulting in a change in the variables x, change in x, change in y, change in u, the system equation can be written in a linearized form here like this. From this equation, here what is this? We had this your x, that is your f, this is your x and u. It is an autonomous system where it is not a explicit function of the time. So from here what we are going to do, let's suppose we want to go for x plus change in x, that's we want to change in the state by changing your function here f, x plus change in x, and your u plus change in u. Now what we can do, from here we can write this function, we can use the Taylor series expansion, and using the first order Taylor series expansion, ignoring the higher order, we can write here this is your fx u plus here this function f over x, and it is your x1 and del x1 and so on, plus here del f upon del u, and here your change in u, and if you x1 to n variables that will be coming to the picture. So what is this? This is your x dot. So from this x dot will be cancelled, and finally we are getting here x dot is equal to some here the differentiation factor, and that differentiation factor I am just denoting as a, and it is your change in x, plus here that is another differentiation is b, and I am representing your u, and this is nothing but our this equation linearized. So what I did, if we are perturbing our state by the perturbing our input, we will just changing from here to here, some there is a small change in the delta x. So x, now we are differentiating this x dot, the change in x dot, now we are coming here, plus this function, and this function is nonlinear, so just we are differentiating, and finally we are getting this value at certain point, and here this is your, so this your a will be the differentiation, partial differentiation of function f in the previous case over the state variable. So this A is called the state matrix. This matrix, the order of this matrix is your n cross n if your n is number of state variables. Similarly, this B is the partial derivative of the function f with respect to input vector, and similarly your y output can be also linearized, and then we can write this linear function is this, where the C is your output matrix and here D is your feed forward matrix. Now these information are very useful. Why this A is square you can now understand. So here just I want to show this matrix A, matrix B, as already I have written. So to see this exactly, this your A matrix is nothing but, I can write here A is your nothing but, it is your, let's suppose we have the different functions, so it is f1 over x1 to here del f1 to del xn to here del fn to del xn here, and del your fn to your here xn. So this is your n cross n matrix. This is a square matrix, and this matrix is very useful, that gives information about your system behavior. So this is your called state transition matrix. Similarly, this B matrix will be here your del f1 to your del u1 to here del f1 to your del ur. Let's suppose we have r inputs here, m I have written, to here del f1 to del u1, here again differentiation of del this is n to here del um. So order of this matrix will be nothing but your n cross m, where is m is your number of inputs. Now this I wrote here, sometimes mathematically it is very simple to see. This is let's f x u, I wrote this, where x is the vector, here this x is vector, is u is vector, this f is also vector. Means here if you want to write here x1 dot, then I can write f1 here x1 to here xn comma u1 to your um. So this is a function of all the variables x1 to xn, u1 to um. Similarly, I can write this x2, here is another function f2, here from starting the variables are xn, and here u1 to your um. So similarly we can have your xn. So all these equations here can be represented in the compact form, and that is called the vector form representation. So here we can write simply, this is a x dot is a nonlinear function of this. So here the differentiation of, for the first matrix here we are getting this much, this f1 differentiation of x1, here f, and the second term is f1 differentiation of here x2, so on so forth, and the finally in this row is the differentiation of f1 with respect to xn. Similarly for other rows we can calculate, and this matrix is n cross x matrix. Similarly the C will be your nothing but your partial differentiation of g1 with respect to your x1, here your g1 partial differentiation of x2, and finally here your g. Now how many g you have, it depends upon your the order of this matrix. Let's suppose you have k g, means your outputs are k, so it is your g k x1 to here g k over xn. So the order of this matrix is nothing but your k cross n. Similarly we can write this D matrix, that is your, it is called the feed forward matrix, which define the proportional of input which appears directly in the output, and the size of this is nothing but your k cross your m, because m is your input, k is your output, n is your state, here k is your output. So it is just a definition that we can define. So from here you can see the order of this matrix here, because this is n, so it is n cross n here from multiplied here. This is a square matrix. Here again it is not a square, this is also not a square, and this is also not a square. So these matrices are used for the stability of the system. So all the derivatives are calculated at the initial equilibrium point, because here the derivative, that is the df1 upon dx1, they are the calculated, these are the values of this A. The matrices, the elements of A are the constant. So they are calculated at certain initial equilibrium point, and it can be shown that the closed loop poles of the above system are roots of the characteristic equation. Here determinant of Si minus A, that is S is a Laplace transform function, I is the identity matrix, and minus A is the state transition matrix. If you get the determinant of this and equating is equal to 0, then the characteristic equation which you will get, the value of these roots will be nothing but your eigen values of the state matrix A. So this eigenvalue is very important for the dynamic stability of the system. To know only these eigenvalues can give the information about your stability of the system. So eigenvalue, that is normally represented by lambda. So if your state transition matrix is n cross n, so your eigenvalues will be your n eigenvalues of the state matrix A of the size n cross n can be obtained by finding the roots of this characteristic equation. This is the same, because once I have replaced S by lambda. Here the negative sign doesn't mean that's a lambda I minus A determinant that is equating 0. So it's the same. So we can get here for any 8 matrix that is your order n cross n, you will get this a 1 to lambda n, means you will get n eigenvalues. So the eigenvalues again here, it may be real, it may be complex. So normally let us represent any eigenvalue I will have a real component, that is lambda alpha I plus j omega I component, which are given by the roots of the characteristic this equation. That is again, that is of system state matrix A. Following conclusion on small signal stability can be drawn. Knowing these, we can draw the various conclusions, and the conclusions, first conclusions that we can draw, when all these eigenvalues have the negative real part, the system is asymptotically stable. Means all this negative real part means here your alpha i's are basically negative, then system is stable. When at least one eigenvalue, at least one, means out of n there may be possibility 1, 2, 3, 4, but at least one, if it is positive, then system will be unstable without any doubt. So for example, let's suppose a system, you have a characteristic equation, let's suppose x square minus 2x plus 1 is equal to 0. Here we are getting x1 is equal to 1 and x1 again x2 is equal to 1, means we are having this eigenvalue 1 as well as 2, both are same, and here they are the positive. So this system is unstable if this is characteristic this. Similarly, if it is a plus, then we will get the minus here, and then we can say the system is stable. When all the eigenvalues have the negative real part, when all, because these values are very important, where at least, all, so you should be very carefully what I am talking about. So when all the eigenvalues have negative real part except one, means all except one. Suppose you have n eigenvalues, so there is a n minus 1, they are having the negative real part, 1 is having the complex purely imaginary values. You must always know these eigenvalues, if they are occurring in the complex numbers, so another will be its complex conjugate. Means if 1 lambda 1 is, let's suppose it is written alpha plus j omega, then certainly there will be another eigenvalue that will be alpha minus j omega. So we'll have the two, that is the pair. So one will be the conjugate of another one. We will get it. In real it is not necessary, but in the complex, if any one of eigenvalue is your complex, so we will have another one that will be the complex conjugate of the previous one. So here this one complex pair means if you are having n eigenvalue, so n minus 2 here are having the negative real part, and the 2 now as a pair I am saying, so 2 will have the, if they are having pure imaginary and that they are lying on the imaginary axis, that is a plus minus j omega, means this is 0, this is 0, pure imaginary means real part is 0, then the system exhibit the oscillatory motion, means system will just behave like here oscillatory motion, and then its magnitude may increase if the something other roots are there, and then it may decrease. So we can again guess what will be the system stability. So here, as I said, this alpha will always occur if it is a complex, then it will occur in a complex conjugate, means alpha plus minus j omega will be the eigenvalue and it will be in the pair. If it is here, the j term is appearing. Now this can be written again, can be simplified, and we can write another factor that is very important, and we can express in terms of damping ratio. Damping ratio is defined here is the zeta, and this zeta is nothing but alpha divided by alpha square plus omega square, where omega is your damp frequency and omega n is your natural frequency. So the frequency of oscillation, that is f, will be your nothing but your omega upon twice pi. So this will be oscillation, and the damping ratio zeta determines the rate of decay of the amplitude of the oscillation. So this determines the rate of decay of the amplitude of the oscillations. What is the oscillation if it is oscillating? So this denotes how much decay is possible. So that's why it is called damping ratio, and then zeta is very, very important. So we can express this whole alpha plus minus j omega in this term, and that is your zeta omega n, means here the zeta and omega n is called the natural frequency, and the zeta is your damping ratio. So with the help of the zeta and omega n, we can normally give the performance of the system. Now let us see, let's suppose you have I can say in this eigenvalues here, let's suppose this is your eigenvalue, this is a real, this is a imaginary, and then you have your eigenvalues that is a complex conjugate, and they are here in this, you can say, left hand plane. From here it is 0, this is the imaginary axis, this is your real axis, then this system will be your stable, and it is called stable system. And if you see the two, because there is a two variables, means two states are there, because the two poles are there, means there is a two. This is basically obtained by state transition matrix, means there is a two, means there will be this matrix order will be 2 cross 2, means you have the two states, and these two states, if you see, their trajectory will be here, it is coming to here, this is coming to here. So it is your Z1, this is your Z1, and Z2 if you draw, then we will have this type of information. So they are converging to this point and the system is stable. Now another possibility, that here this is your j omega axis and this is your sigma axis. Sometimes it is here we are calling alpha, so it is your alpha axis. So if your eigenvalues are in your right hand plane, then what will happen? The system, it is called unstable here, and this will be no doubt here in this case it will be also oscillating, means if your poles are lying on here this imaginary axis, means there is a possibility here, this is your j omega, here it is alpha. If you are having here your system response will be decaying, means with free response, if you have perturb, there is no force, so a system will come to the 0. But here if you are having this, what will happen? In this case it will be oscillating, and it will be the oscillation will be keep on down, because here it is the negative, that is a damping. So here we have the minus alpha 1 and the minus alpha 2 here as well. So it will be the oscillation, but it will be decaying. In this case there will be oscillation, and here it will be keep on increasing, and the system is unstable. For this case, if it is this axis. If your this roots here, they are lying here, then your system will be simply, it is going out of bound. It will be not oscillating. So oscillating means if they are having some complex, means you are having some imaginary term, and that is omega. As I said, it is nothing but the frequency of oscillation is omega upon 2 pi. So if your this omega is 0, that is this axis, then there will be no oscillation and is a direct decay will be appearing. Another, as again here I have, this is unstable, this is the case, this is your unstable case. Another is if your poles or roots are lying on the imaginary axis here. This is your imaginary axis, here it is your real axis of the root, then it is called your vortex and it will be a continuous oscillation. Means here it will be oscillating and it will be neither decaying, neither it is rising. So these things are also not required. In the power system, we want that it should decay and there should be some damping. Otherwise, what will happen? If there is another small perturbation, the system will go out of step. Now, another condition may arise that if you are having the real poles, roots or eigenvalue, sometimes it is called poles, sometimes called the eigenvalues. So everything is same. So if you are having the two, one is in right hand side, another is in your left hand side, then it is called your saddle node. And this is again is unstable at that point. So to analyze the small signal stability, the modal analysis is performed, and this modal analysis is very, very important for seeing the system behavior and to guess whether system is dynamically, or you can say small signal, stable or not. Associated with each eigenvalues, as I said, if your state transition matrix A is of order n cross n, there will be n, this lambda I will be n in number. So there will be two eigenvectors. So for corresponding one eigenvalue, there will be two eigenvectors, and they are known as the right eigenvector, that is REV, and another is your left eigenvalue, a vector, that is LEV. So these vectors are very, very good for giving lot of information. Basically, the participation analysis they normally provided. So how we can get it? We know this A transition matrix. Here, if you are going for the right eigenvector, if you are using some vector phi, and that is satisfying your eigenvalue I, here phi I, for I here, this is for all phi. What is happening? This phi will be nothing but your, it is your left, right eigenvalue, eigenvector, because it's a right hand side here. You can see. Just we are multiplying this vector. Why it is vector? Because here phi will have again order for 1 to here. This is your again this n, and it will be transpose. Because you can see, if you are multiplying here n cross n matrix, you want here this is n cross n, here this is a vector, this is your constant, and this is a vector. What is happening? If you are going to multiply here phi this side, that is your phi 1 to your phi n, this is n cross 1, then you will get n cross 1 vector here. So basically, we can get the phi 1, phi 2, phi n, these elements of that vector. So for corresponding each eigenvector, eigenvalue, we will have the two eigenvectors. One is called your right, means these are calculated, they are satisfying the equation here by putting this. By putting this, we can calculate. Another is called the left eigenvector. If you are using another vector here multiplying with your transition matrix, for that corresponding eigenvalue, and you are putting here, you will get another vector, that is called left eigenvector. And no doubt these two vectors are orthogonal to each other. Means if you are multiplying here this vectors phi and psi together, r psi into phi, you will get an identity matrix, and the order of this identity matrix is again n cross n. So this is very, very useful analysis, that is called modal analysis. Normally we perform for the linearized system for linear system. So our power system is not linear. So what we go for that, we normally we linearize around this operating equilibrium point, and then we can go for other analysis. So based on those vectors, we define the participation factor, and that is very, very useful for obtaining the modes. So the participation of an ith mode in kth state is defined as the here pki, and that is equal to your this phi ki multiplied by your psi ki. So this is here you can see for the kth state, for any kth state, means we have the n state. So for that any kth state, ith mode we want to get, so it will be phi I ki into here psi ki, that we can multiply, then we will get this element. And that here, that vector will be again, there will be n modes, and we can get this is the P is your participation matrix. So this represents phi ki. It measures the activity of kth state in ith mode. This gives information that kth state, how much they are basically active in your ith mode. This psi ki weighs the contribution of activity. It gives the contribution of activity of kth state in ith mode. This provides the measure of activity. This weighs the contribution of activity. So the pki is a measure of the relative participation of kth state variable in ith modes of oscillation. So this participation factor is normally calculated, and based on that we normally see the behavior of the system. So let us see the single machine infinite bus system for the small signal stability analysis, and here I am going to use the classical model, where we know that we have to represent the machine by simple second order differential equation. Here the two you can see here, and in the classical model there is a lot of assumptions, as I explained in the transient stability case, where we have to take the PM is constant, that is a mechanical input is constant. We have to represent the machine behind its source and its equivalent impedance. So these are the various assumptions, and we can have the H, that is the inertia constant of machine. Means here a single machine infinite bus system, let's suppose you have a generator here, and this is connected with your, let's suppose, two line, and this is your infinite bus. So this generator having your inertia constant H, again H in second. So that's the swing equation that we considered earlier. Considering the damping, here this Kd is your damping constant. We can write this H upon 2F. Here differentiation of double differentiation of angle delta plus Kd change in omega r is equal to your Tm minus T in the per unit torque system. So it is in per unit we have written this, but if we are writing in actual quantities, it is different. And then we can linearize this equation, and first linearization we can get, as you know, just we have represented this two equation as here x. X is nothing but your here what I said x1 and x2 variable, and I said here this x1 dot is nothing but your speed, and your speed here x2 dot is your this differential equation. So we can get the two variable here, that is your one is your delta and another is omega, and we can write the differential equation corresponding these two. So this second order differential equation can be linearized, and we can get two first order differential equation. Here this is a differentiation with the reference to omega r. Omega r is nothing but it is your relative, is a per unit speed. Kd is your damping constant, H is your inertia constant. This change in omega r, here Ks is your synchronizing torque, and that is your divided by 2s multiplied by your change in delta. So here this omega, this change in omega r, it is nothing but your speed deviation in per unit in pu, and that is defined as your omega r minus omega naught divided by your omega naught. So this is this value. Your H is of course in second, Kd is the damping torque coefficient in per unit torque divided by per unit deviation. However, your synchronizing torque coefficient in per unit torque divided by radian. So we have included the damping coefficient here as well. And now this Tm, why this term is appearing at all? This term is nothing but if you are using the differential form here, so there is a change in Tm and there will be change in Te due to the change in, if you are perturbing slightly, there is a small deviation, a small disturbance, there will be change in mechanical input as well as electrical output. Here in the classical machine we have assumed that there is no change in power input, so this value will be 0. So only we are getting this Te, that is Te change in that Te. What is this Te? This Te is nothing but if you are differentiating this Te, means we can get the change in Te. Here Te will be your Te your in delta into d delta. So the change in Te will be in the per unit. The Te will be equal to your Pe and it is your E into V divided by x sine delta. So this is your V angle 0. Here it is your E angle delta. So these are the two voltages of its internal voltage, and X is your total impedance of the system, including transmission line, including generating transformer if it is there, and the internal impedance of this machine as well. So this X include completely. So what if you are differentiating this term with reference to your delta, we are going to get here, I'll show you here. So change in your Te will be your, here I will differentiate this P with reference to your delta and then it is your delta. So what is happening, your E V X cos delta and this is your delta. So this term is nothing but your Ks, and that is known as the synchronizing coefficient or synchronizing torque coefficient of this Te. So this we can write here. So in this equation I have used here, you can say Ks term that is appearing, and the 2H here it is coming from that side. So we can write in this linear equation. And another linear equation, as I said here, x2 dot, it is nothing but your omega now. X2 is nothing but here what we are going to get, this d delta upon dt, it's your speed. So if you are changing here, it is your this and this will be this. But this is we are writing in the per unit, this in the radian, so we have to multiply this to get the radian. So this we are multiplying in the actual speed, so we are getting actual here, the change in actual speed, because this omega r in the per unit. So we have multiplied so that we can get the change in omega r in actual value. So we are getting the two here equations, and these two equations can be again written in this block diagram, that is a linearized model of synchronous machine. So from here we can write the transfer function of this in terms of Tm, change in Tm, and changes here change in delta, and then we can analyze what will be the behavior of the system following any disturbance. Here we are having the two states, one is this, another is this, and we can write this equation in the state space form. Here I can write here the state space form, means this is your d upon dt, and here just we are going to write is change in omega r, here change in delta, that will be equal to your again 2 cross 2 matrix, and here again our state will be your this omega r, here change in delta, plus we will get a vector that is a B matrix, and here your change in Tm. This change in Tm now here we are going to get, if you solve that, you will get this, here it is 0, here you will get omega naught, here you will get 0, and this component you will get this Kd upon 2H, and here it will be your Ks upon 2H with the negative sign. So this matrix is your A matrix, this matrix is your B matrix. Now to analyze, to see the eigenvalue of this matrix, you know, as I said, we can simply write here lambda I minus A if we will get the determinant, and that will be equated at 0. We will get the 2 lambda. This is a 2 cross 2 matrix, so we will get 2 lambdas. So now what we can do, we can go for the determinants of this. So lambda I minus this means we are going to get lambda here plus kd upon 2h, this matrix one element, here minus minus it will be plus, here 2h, this will be your minus omega naught, and here it will be 1, and that will be equal to 0, means the determinant we want to calculate. Sorry, here the lambda again, sorry, is the lambda. So lambda here it is A is 0, so lambda will be there, and then we have to solve this. Means we can write here the characteristic equation. This will be lambda plus kd upon twice h, here plus this is a ks over 2h omega naught is equal to 0. So now you can see this we are getting a quadratic equation. This quadratic equation we can solve, and now it will be your lambda square plus kd upon twice h lambda, here plus your ks omega naught over 2h 0. Now if you will solve, you will get the two values of lambda, lambda 1 and lambda 2, and by solving this you will get the two roots, you can say two roots of this machine, and then we can find out the values of lambda 1 and lambda 2. Now if you write here lambda 1 is a simple, we can write here from looking at this equation, it is minus b, means is a minus kd upon twice h plus minus square of kd upon twice h square minus 4 ac, here it is minus 2 ks omega naught over h divided by 2. So here you can see this will be the imaginary term, and we will have the two roots. So we can now write this undamped natural frequency for this system, or this system we can simplify in terms of your lambda square plus twice zeta omega n s plus here omega n square 0. So this is your natural frequency. So this gives your natural frequency of the system, means I can write here I can write, means this your omega n is nothing but is under root your this ks omega naught over twice h. So this is your undamped natural frequency of this here, and these two values will be equated at this. So we can get from here omega n is this, so we can get the zeta, and this zeta will be your half kd over 2h omega n, or we can write here it will be your kd upon 2 under root ks twice h omega. So this is now the different value of the kd and the ks. Now you can see your zeta will be changing. Now to see this, here again I have written here this natural frequency here will be your this, and your damping ratio will be written as again I have written. So from above characteristic equations which I defined, the second order with the two eigenvalues having undamped natural frequency this and the damping ratio this. So as synchronizing torque coefficient Ks increases, from here you can see if the Ks increases, the natural frequency increases and the damping ratio decreases. Means once Ks is increasing, Ks increases, this shows your omega n increases, however your this damping ratio is decreasing. So what is happening? For this it means if your system here it is just oscillating. Now if you have reduced Ks, so this frequency is increased and damping is reduced, means your system will be undamped, and it will be again this is very huge frequency, means large frequency will be appearing, and again it will be the damping will be less, means it will be for longer period. For example, if your here the system is, let's suppose, decays in the 2-3 cycles, 2 cycles, here it's 1 cycle, 1.5 cycle. So if you are increasing this K, what will happen now? This will be now coming to be here several, and also your damping will be going for the longer period. Means the damping coefficient reduced, means it will take longer time to damp out. So this one property with this Ks. Now an increase in the damping torque coefficient, this Kd, suppose if you want to increase the Kd, what will happen? This increases the damping ratio, you can say it directly, and it is independent on omega n. So it is not changing your frequency is a constant, but your the damping ratio, this is improved, means damping torque coefficient increases the damping ratio, whereas an increase in inertia constant decreases both omega and this theta. So from here we can infer several information. For example, if your Ks is less, what it does mean? Your natural frequency is less, your damping ratio is very, very high. So this Ks is less, means damping ratio is increased, means your system is damped out, means your synchronizing torque Ks coefficient is less, then decreases, then this is increasing, but and at the same time this is also decreasing, and your system may be simply here without oscillation, it may be damped. Now if your Kd is increasing, your damping ratio is increasing, and that's required that it should be damped out, your oscillations must be damped out in field cycles, and that is good for the system stability. At the same time you can see this H value is also very important. If you are increasing the inertia constant H, this shows that for H increase, it is showing your omega n is decreasing, and at the same time here your damping, it is also decreasing, both are decreasing. So the damping decrease is something that it will be oscillating for larger time, and the frequency decrease means again the frequency is less, but it will be the damping, this is not required. So that's why if your system, your machine is of larger size, means if your H is more, this oscillation, the cycle of oscillations frequency will be less, but the damping will be, due to decrease in the damping, here it may take longer time. So these are the information for the two machine system. Now normally to damp out the power system oscillations, those are always present in the power system, we normally use power system stabilizers. So power system stabilizers, basically they are very, very useful for improving the dynamic stability of the system. So it helps adding damping to the rotor oscillations through auxiliary signal to the excitation circuit. In the previous lecture, I was just drawing a excitation, this DC excitation type 1, where I said there will be one auxiliary system that is coming from the power system stabilizer. So that signal basically given by the power system stabilizer, and it is adding some extra signal to your excitation system. To produce damping, the stabilizer must produce a component of electrical torque in phase with the rotor speed deviation. Because we know that here your the change in the TE, it is the two term, your, as I said, this Kd omega plus here your Ks omega, Ks del delta, means the torque is having the two component, one is your damping component, this Kd, and another is your synchronizing, that is changing the angle. So what here means, as I said, so to produce the damping, the stabilizer must produce a component of electrical torque in phase with the rotor speed deviation. Means we have to add this Kd, we want to give the damping, so we have to add some signal here that is in phase with this component, so that if this Kd will be more, damping will be better and the system stability will be enhanced. It has three main blocks in the power system stabilizer. It has the gain, phase compensation, and your washout circuit, or sometimes it is called reset. So you can see the figure first. Here this is a basic model of power system stabilizer. Here this is your terminal voltage ET, RV I was using, and we have the some terminal voltage transducers, those are measuring the voltage, and we can write some first order differential equation. transfer function 1 plus STR, TR is the time constant, and that signal is coming to here. Now this V reference is the voltage reference setting of the terminal voltage of the generator. Here this is your power system stabilizer signal that is coming here. So these two signals now with the measurement signal of the actual terminal voltage here compared with the this, and then it is given to your excitation system. This is your exciter, and its a gain, or you can say transfer function, is written as GEX. And finally it is giving your EFD, and that EFD is the voltage directly proportional to the current, and it is changing your excitation voltage. So this PSS, now this is your PSS blocks. We have three components. One is your gain, that is called K step. Your washout filter, here it is a ST omega divided by 1 plus ST omega. T omega is the time constant, and here 1 plus ST1 over 1 plus ST2 power n. This is the lead compensation we normally use. Now what we are measuring, the input to this is the change in the speed deviation. So this speed deviation we are trying to provide in the phase, we are adding some damping to the system. So we have the three blocks, and these three blocks are nothing but, first one is your gain. The gain, it should be the computed at the frequency of oscillation. The value is also very important to decide these gains. So and should be enough to make damping coefficient positive. So we have to make the damping coefficient this KD positive. If this damping is 0 or negative, the system will be unstable. We don't want that. So we want to make the damping coefficient positive. We should add this signal, gain should be in such that it should try to make the damping coefficient positive. Another is your phase compensation. Phase compensation provides the appropriate phase lead to compensate for the phase lag between the exciter input and the generator electrical air gap torque. So it is basically appropriate phase lead to compensate the phase lag between the exciter input and the generator electrical air gap torque. In practice, the two or more first order blocks may be used to achieve the desired phase lead. Normally we go for here several, not one, several terms, normally one or two blocks we use for giving proper compensation. Another is your washout circuit or reset circuit. It is a high pass filter which blocks the interference of PSS during the regular function of exciter during the steady state operation. So during the steady state operation we should not bother, and it is not used. So it is a just high pass filter which blocks the interference of power system during the regular function of exciter during the steady state operation. Its time constant is large. It allows PSS to act only during small frequency oscillations. So it is not for the high frequency, it is going for only small frequency oscillations. It is, as I said, this oscillation is not more than 3 Hz. So this is only used for that oscillations. If there is a other oscillation, it is not used for. So this is a washout filter here we have used, and its time constant is T omega, and it is set in such that it should work properly. Now for this complete system, again we are having, you can say, the different states. Here we have another state. Here we have, if you are having several blocks of this, then you have the other states here as well. You have another state. So we are just basically what we are doing, we are adding more differential equations, nonlinear differential equations, and those must be analyzed. So to see this, the dynamic equation here, now we have added the three, again the differential equation. One is corresponding to the gain of the PSS. Here what is that? This is nothing but your, you can see, corresponding to this. The gain which is omega is coming, this gain is coming here, and that is your x1 we are getting here. So this time constant etc. they are going to be added, and you can see we are getting the T upon T omega x1 k PSS, that is gain of PSS, and changing, that is the input which is coming there. Now this x2 is now again we are getting from T2 and T1 just we are getting, and this x3 if you are using more time constant and so on and so forth. So you are keep on adding the differential equation corresponding to that. Now this is very, very important, again the tuning, that's the gain and the time constant of these power system stabilizer. If they are not tuned properly, they will create, even though they are used to stabilize, to improve the dynamic stability of the system, they will certainly give the adverse impact and they may sometimes destabilize the system. Most of our Indian power system, all the generators, they are equipped with the power system stabilizers, but still they are not connected to system because their gains and the transfer, this time constants are not tuned properly. So they were creating some sort of more oscillation than they are not connected to the power system. So the tuning of these parameters of the power system stabilizer is very, very important. And for that there are so many literatures. As I said, you know, the power system, it is keep on changing, and once it is keep on changing, all the parameters are changing, and the setting of these parameters of the power system may not be useful for other one. So we have to tune these power system stabilizer parameters properly for the stabilizer. In the next lecture we will see how we are going for the tuning and what will be the impact of these power system stabilizers. Thank you.